Okay, any questions before we start? Did you all receive emails this morning? Maybe not. I think the AI for ER students might not have received emails with AWS account details.
Should we use those details or set up our own?
Quite happy for you to set up something if you would like to, but there's this issue about credit cards and payments. We've created those details so that you've got an account you can use to do the lab. Yeah, so use those details is the idea. But if you have some reason you don't, it's you don't lose marks for not using those details. Yeah, I think for students who aren't on the computer science tripos, they won't have got that yet, I suspect. But email me if you're in that position with a helpful thing like AWS account details in the subject line, so I don't lose the email amongst the lots of emails I get, and we'll make sure we get it. Okay, other questions? Great. So today I want to sort of continue where we were last time in sort of talking about some of the challenges, having given you the sort of context of data science and the data science landscape. So what's going on, what we talked about last time is this background of this term that I'm not that keen on, but it's kind of useful to capture. This idea is this notion of big data. So data becoming a pervasive phenomenon that affects all aspects of our activities, and data diffusiveness becoming both what I think of as a challenge and an opportunity. So the wide availability of data, and so for example, I was involved in pandemic advice, and there people had lots of schemes about how we can use mobile phone data to solve COVID, very few of which actually worked because it's quite difficult to use such data. But some of which, for example, like the Zoe app, which was an app for people reporting their symptoms, we were able to allow ourselves to get a better resolution of COVID distribution within the UK by combining that with surveillance data from the ONS survey. So I don't know if you've ever seen this thing. It's the sort of thing that you see if you're a business student. Is this thing called the Gartner Hype Cycle. So the idea is it's a sort of visibility or level of interest in a subject area. And the idea is it comes from this sort of technology trigger. So some new technology emerges and then everyone's, oh, this is going to fix everything. Ah, and then, oh, that didn't fix anything. And then it's like, oh, actually it just sort of, so with a computer, we're somewhere here, just the computer itself is constantly doing cool stuff. But I was very lucky. I think they're online now. There's something called the Silicon Factor, which was filmed in the late 1970s, where it's people talking about how the silicon chip is going to revolutionize manufacturing. And of course, it totally has come true. I mean, everything they say there has come true, but it took a long time from the late 70s for it to become true in the way that that they are describing. And it's the same with AI data science technologies. So I like to do this sort of exercise of sort of saying, well, where are some of the terms? Oh, sorry, I meant to update this for this year. You can you've got the notebook, so you can re-update these trends. I've been running them for a number of years to see where a few different trends are on the AI, on the Gartner Hype Cycle. Now, this is artificial intelligence, which interestingly was sort of being searched for a lot there and has gone through some sort of plateau and then has gone up over the last few years. We'll talk about some aspect of this plot in a moment. I want you to be skeptical about this plot and tell me what's funny about this plot. Here's another one. This is this term big data, which even before like the big sort of convolutional neural networks result that came from neural networks and triggered a wave of interest in machine learning, neural networks, deep learning, was published in 2012. So this big data takeoff is occurring before then. In fact, there was a paper called 8 Great Technologies back in 2008 that was identifying this phenomenon around big data, and everyone started saying big data. Like basically no one said big data until what, about 2011 and a half. And then data mining, I find this very interesting because look, back in the old days, everyone used to be going on about data mining all the time. And that was like, it was like a massive, when I was doing machine learning, the data mining community was sort of better known than the machine learning community back in 2005. And what I find interesting, how would I characterize the data mining community? Because their objectives are very similar to what we're trying to do with modern data science or machine learning. I think quite an interesting difference was, or is, that data miners often are database people who are trying to extract information from a database. So often they're expressing their data mining in SQL queries, which turns out to be quite a restricted way of doing analysis, but of course it's very fast. So I think particularly back in the day, that was a sort of very major approach, sort of approaches to sort of understanding things from large data lakes that you could get through database queries. Oh, not finished yet. Now deep learning. Now what is interesting, as I said, is that the technology trigger for this is around about 2012. So these are, so I should have said Google Trends are, if you haven't seen them before, they're how much people are searching for these things. And I think this is worldwide. It might be North America. You can again check on the code. So it's how much these terms are being searched for. And what you see is that there's this big sort of leap in deep learning that, interesting, is starting to tail off. So it surprised me last year when I first saw that. That was the first time I saw that tail off, was last year. So it's a shame I didn't rerun it, but as I say, you can rerun it to see if that's continuing to tail off. And then machine learning, which again, it's interesting, it's starting to tail off. Now, what's funny about this approach? I'm trying to teach you data skepticism. What's very odd about this plot? What thing should you find surprising? I would normally say machine learning is the principal technology underpinning artificial intelligence. If I say that, what strikes you as odd about this plot? It's overtaken AI. And why do you think that is? What have I done in this plot that means that that's the case? Precisely. Yeah. Yeah. If you search for AI, you'll find that AI blows away all of these and they all fall off the scale. So be very careful with data, right? Because unless you think a little bit about it and whether that makes sense, and often you have to use your contextual knowledge. So the reason I don't rerun this with AI and ML is because AI, if we did rerun it with AI, you wouldn't see anything else. Because one problem is, of course, AI is picking up searches for like people looking at films and things like that. You know, it's a very popular term. So it's quite hard to sort of say how interesting, you know. So this data is, in a very real sense, qualitative, not quantitative, because as was precisely pointed out, you could also search for ML or other terms, and at which point do you stop? It's quite, these decisions affect the results you get. So a little bit of data science on data science, or metadata science, as I used to call it before Facebook renamed themselves. So what is machine learning? Because I do say machine learning is the principal technology that's driven this recent wave, because there was clearly a previous wave, right? We can see AI was up here when, well, machine learning was a little bit up, but data mining was up, right? So what is this technology? Well, I like to phrase it this way. You'll see me phrase it. If you see me talk, I'm always sort of coming up with this little formula that machine learning is the combination of data with a model through computation to make a prediction. Now, we could say that a lot of fields are related to this. So we could talk about statistics being like this, or we could even talk about physics being like this. Physics is, the physical laws are a model of the way the universe works. But I think the choice of terms is quite important here, that there's very little in this little formula about interpretation. And that was very important at the founding of the field. So in statistics, you might do the same thing as this, but you're not just interested in prediction, you're interested in explanation. So statisticians will focus very much on trying to understand the truth of the world rather than make a prediction. Whereas a machine learner is happy with the fact that if you show this advert to people, 0.7% of people will click on the ad, and that's a good prediction of the actual percentage. Doesn't care why they click on the ad. A statistician might be more interested in, something like, what are the demographics of the, is this an age related? Is it younger people that click on the ad or older people? So that actually affects the type of models you use, and actually has now downstream effects in terms of when you look at the problems machine learning faces now, because it constructed models mainly around the idea of prediction. And so many of the problems we face in society are around the interpretability, the fairness, the understanding, the accountability of those models when used in practice. But it did sort of release machine learning researchers from the sort of burden of having to always design things which are predictable, which are interpretable. So that's how you end up with models like neural networks, which would be which work great in terms of prediction, but are quite difficult to interpret or provide explanations for, or traditionally were. It's the sort of thing people research now. So the data could be observations, and they could be actively or passively acquired, right? So data comes in many, many forms. So the surveillance data is when I go out and I randomly collect data, like for a randomized controlled trial. So I acquire data specifically to answer a statistical question. And that's the sort of data that emerges from this era of classical statistics to get over the lies, damn lies, and statistics, right? If I do, when we do COVID, surveillance studies were done in terms of randomizing who's tested, and you spend a lot of time making sure that you're testing a random subgroup of the population. That doesn't work if you're sending text messages out to people saying who would like to be tested, right? That's an easy thing to do, but you're going to get certain sections of the population over or underrepresented. So that observation data is just where you look at the world and you try and take data from the world, like we just did with the sort of Google Trends, and try and draw conclusions from that. And drawing conclusions from observation data is very, very hard. And then I use this term happenstance data. So observation data also sort of has this implication that you actually cared about those values. So you actually explicitly went out and started trying to measure things, which is the way things used to be. But I think the new challenge is what I call happenstance data, which is people are just recording data without any purpose in mind. It's so cheap to do now that a lot of the data, almost all the data we have available is just, well, it's there. Yeah, we could put it on the disk. It's log files, no purpose in mind at all. And that creates a lot of the problems we're facing around data science and how to assimilate that data. So it should be useful. All companies are telling us there's value in this data in practice. So the model is the assumptions we bring in. And so those assumptions in machine learning and statistics are often things like smoothness assumptions. So beliefs about the regularities of the universe. I get to do a thing I couldn't do in the pandemic now. I used to say, if I were to disappear from here and reappear over there, you would be surprised, right? If we were doing it over Zoom, you wouldn't be surprised. You would think Neil's camera froze. But if I were to do it here, you would be surprised. That's a smoothness assumption, right? That I will move in a certain speed, right? Smoothness assumptions are really, really common. Assumptions around linearity of systems are quite common as well, so that things are linear. What's interesting about neural networks is they are introducing new and interesting inductive biases, quite powerful inductive biases, which we're combining with enormous amounts of data. So actually, say powerful, I probably phrased that incorrectly. I think probably the thing that's going on, and you have to attend the Deep Neural Networks course to hear more about this, is that there's a very weak inductive bias in a neural network, but they can allow the data to speak in some sense. So when you get enough data, the data get to sort of say, well, this is how we're forming. It's beyond your sort of simplistic idea of what smoothness looks like, because it's incorporating all these sort of features that we've derived exist. And once you get to this feature level, yes, then it's smooth. But you first of all have to work out that there's all these aspects like features to the words and so on and so forth. And that's what neural networks are managing to do, which is massive, right? Yann LeCun used to stand up, I've known him since 1997, or seen him speak since 1997. And he's been saying that since before I knew him, that with neural networks, you could learn features. But even he would never have claimed the extent to which that is true in terms of what we're seeing now, in terms of like large language models and DALL-E and all that sort of stuff. He would never have dared. I mean, he was just saying, oh, this could be better than your existing computer vision algorithms, which is what those methods became in 2012, but utterly dependent on data. How much? So the big breakthrough result was convolutional neural networks applied to a data set called ImageNet and doing object detection on that. Do people know how many data points, labeled images there were in that data set? Loads, yeah. 14 million. 14 million labeled images. The real breakthrough in that data set is Fei-Fei Li, who led the study, realized that you could use a new tool to label the data. Up until then, there was a big Pascal. It was a network I was involved in, and Chris Williams and others based in the UK, Visual Object Challenge, where they labeled data because they realized that labeling data was the big key. And also at Caltech, Pietro Patrono, who was worked with Fei-Fei Li at Caltech, realized this early on, that labeled data sets were the key. But the scale of data sets they could label by getting sort of grad students to do labeling was in the sort of thousands, right? And Fei-Fei decided she really wanted to break the mold and go beyond this, but then she worked out how many hours of grad student time this would take and discovered it was implausible to fund it. What did she use that enabled it to happen? People know? Mechanical Turk. Yeah, no, Mechanical Turk. So it's Amazon system for deploying boring tasks to people, to thousands of people. So she set this up as a task on Mechanical Turk, and thousands of people completed this labeling task. And interesting, of course, we didn't get the machine learning models to work initially on that. It took a while because they weren't capable of assimilating all this data. And then it was convolutional neural networks was the first architecture that could assimilate all this data and made breakthrough results on this. So what you're seeing when you, sometimes I think this isn't intelligence in any form. It's copying, you know, it's copying at a vast scale. It's like, particularly that example, it's enormous amounts of human labor being codified. Like, so you think, well, what's the equivalent in programming hours? But of course, the thing is you could get regular people to do this. And all big tech companies now have vast fleets of people labeling things the whole time, which is a bit depressing. Anyway. And then prediction is the action to be taken or categorization or a quality score on the item, right? So that's what I think of as machine learning. And there was a report that was convened by Jess Montgomery, who works in the university here now. Well, convened by the Royal Society, but she led it on behalf of the Royal Society, called Machine Learning, the Power, and it's off the screen, unfortunately, but you can find it in the link there, which talks about, I think it's still one of the best reports on machine learning. And it's funny how old it is now. It's about 7 years old, but it was written before the hype hit big. So it's it's missing things, obviously, but it talks about the fundamentals. So to combine a model with data, we need two things, I think. This isn't universally true of machine learning algorithms. There's machine learning algorithms that don't work quite like this, but most work in this way. You have two things. You have a function, a prediction function, which is a mathematical function that includes our beliefs about the regularities of the universe. So it includes smoothness, or it includes, in convolutional neural networks case, it includes translation invariance, which is the simple idea that if I do this, I'm still a person, right, as I do it. Yeah. And also if I go up, but I can't levitate, so I can't demonstrate. Well, I could try, I can do that. Yeah, I'm still a person. But interestingly, convnets don't include many other invariances, like the fact that if I rotate myself, I'm still a person. That has to be learned from the data, which is one of the reasons why they require so much data. And people do things like data augmentation, rotated images to help that. And an objective function. So the objective function defines the cost of misprediction. So it sort of says, okay, you predicted that, the truth was this, this is the number that you pay. And then basically machine learning works by adapting the parameters of the prediction function, by looking at the objective function and how it deploys on training data being data taken from the real world, which in machine learning, we're not that fussy about whether it is surveillance data, observation data, or happenstance data, which would make a difference between us and the statisticians. And the reason we're not fussy is because we're not going to care that much about the parameters or the interpretation. Well, that's the way it used to be. Of course, now that everyone's using machine learning, there are a lot of negative consequences about working in that way. Now, machine learning is not the be all and end all of data science. As a data scientist, you also have to become familiar with classical statistical analysis. So these remain more important than ever. My analogy is, it's a bit like, you know, why people know what the reason they worked on graphical user interfaces at PARC was? What was Xerox worried about? That they had a research center working on graphical user interfaces in California in, I think, like as early as the 1960s. What were they worried about? No, in this case, not. Everyone was worried about nuclear weapons. But I think specifically in terms of what their business was going to be affected by. So Xerox, do people know what Xerox used to do? Photocopiers. So what did Xerox think was going to happen when computers took over? No one would use paper. So they thought, oh, we should get into computers because no one's going to use paper. Do you think usage of paper went up between the 1960s and the 1990s or down? It went up massively, because printers meant people were using paper more than ever. And I think I even checked it. I checked it a while ago. It has begun to go down now, but actually I'm sure it's still well above the 60s, you know, because computers existed, paper could now be produced in vast reams, and still paper, like I just did a thing earlier, and I still preferred to print. Now, it would take me quite a while to write that, right? But it takes me 2 seconds to print it. So in the same way, I have the same analogy for classical statistics. Now we're doing more and more analysis than ever because there's more and more data than ever. I don't think the day will ever end that classical statistics isn't a massively important tool for sanity checking. And sometimes I think it's enables us to visualize our analysis bugs. So having that sort of understanding of statistics, which you're not going to teach a great deal in this course, but that understanding of statistics, in fact, I'm going to sort of refer you to a book, if I get that far on the slides, to help you get that sense of data and the pitfalls data throws at you. That's a really important component of a data scientist. So all machine learning is doing is automating by scaling and codifying processes. So almost all, well, any generation of automation, what it tends to do is look at a process like making a gun and saying, I can decompose this process into various parts, and then I can do those parts efficiently by specializing around them. Right? So this actually, Babbage, who will know because he invented an early mechanical computer, his main work at the time was also talking about the efficiency of production lines, right? So people all the way back then were saying, how do you make production lines more efficient? And one of the ways you do it is you decompose the components of, you decompose the process of making, say, a gun or a car, because Colt 45 was an early production line that is famous, and Ford Model T in terms of cars, and make it more efficiently and automate where you can. So modern car production lines are automating enormous quantities of that process. Machine learning is just doing the same thing. It's looking at a small compartmentalized intellectual exercise very often and saying, well, I can codify this process by watching humans do it millions of times, or seeing what humans generate from this if it's unsupervised learning, and copying it, right? And creating something that copies it. Not by programming like we normally would do, but just by this process of learning. And so it's certainly, as I say, it's not all the be all and end all of data science, but it's just the emergent thing that's come from this world of data. The methods we're using in machine learning, as I say, they've been around, some of them for 25 years. Of course, we're refining them now, because when I came to the Newton Institute here in 1997, to attend machine learning summer school, like half of the world community was here, and there were only like 200 of us. So now, if you go to the main machine learning conference, there's 16,000 people. So obviously, like, they do more stuff, but the basic ideas were still there back in the day. So it's really this world of data that's changed everything. So how do you codify something? Well, we might want to understand the probability that someone buys a sweater online. And this is the sort of thing that you're effectively doing. And actually what I've drawn up here is a statistics model as well. So what I have as a little thing that if I use parameters with the letter beta as the parameters, I'm doing statistics. So I care about the interpretation of the parameters. If I use W, I don't care about them. And that's how I sort of show people I'm trying to do statistics or machine learning, because the tradition in statistics is to use beta for parameters, right? So if I care about the meaning of these parameters, so I could care about why people buy a sweater. Is it because they're like, look at me, I wore my sweater today, it's cashmere. Do I buy it because I'm getting old, as I am? Or do I buy it because I live in the north, as I do, right? Even though it's unseasonably hot. Or do I buy it just because I was trying to look smart for you? So we could say the odds is the sort of thing we typically look at, the probability of buying divided by not buying. And that, since that's a positive number, we apply a trick we often apply to positive numbers. We look at the log odds. And this is called a generalized linear model. You're going to learn more about these with Carl Henrik towards the end of the course, because you're going to use these type of models in your analysis. And here, what we're saying is, like, if age is high, the log odds go up. And if log odds go up, the odds go up, right? Because log is a monotonic function. So if age is high and beta is positive, then age is positively correlated with sweater purchase. Similar, if latitude is high and beta is positive, then latitude is positively correlated with sweater purchase. So that's the sort of thing a model could encode. But the interesting difference between statistics and machine learning, in statistics, you care about the betas, and in machine learning, you care about the quality of that prediction, the calibration of that prediction, and don't really care about how you formed it. So you might start doing things like, well, I'll consider age times latitude. That would be a polynomial model with a quadratic term, right? And age squared and latitude squared. So that loses interpretability a bit. As soon as you start doing that, you start getting these nonlinear features. I mean, there's still with a polynomial thing, it would be an interaction term. There's an interaction between age and latitude. It wouldn't deal with the fact that if you're in the south, if you're in the deep south, if you're sort of like in Antarctica, you probably also buy sweaters. So latitude is, you would need a negative term. So it doesn't deal with that nonlinearity. But this is the type of way we would write this model in machine learning. We would say the probability of buying something is a sigmoid function of these. That's the same model. What we saw before is the way a statistician would tend to write it as a generalized linear model. But in general, and as a linear model, it's a linear model because it's linear in the parameters here. So beta transpose X is it's actually a generalized linear model because that's a nonlinearity. But the form of the generalized linear model is a nonlinearity around a linear model. But in general, I might just want to say, well, let's throw that specific class of models away and talk about a general prediction function. So here, f of x comma beta. So we're saying that the output in this case, if we're just going back to regression, so I've got the nonlinearity. So the number of sweaters we might expect to be bought in an area is a function of some set of features and some set of parameters, a nonlinear function. And then that would allow us to capture the fact that people in the South also like to buy sweaters, or that there's some nonlinearity that, you know, it's not like that children are made to wear sweaters, so maybe they like to buy them. I don't know. Where f of x is the prediction function. And then for the objective function, if we're doing regression, a common one would be least squares. So I mean, this is sort of high school. If we do a linear model and do least squares, then that's y equals mx plus c. But everything else sort of extends from the same idea. Least squares is a particular objective function that can be motivated in various ways. But one of the reasons it's very popular is because it's analytic, in the sense that if you do a linear model with a least squares objective function, you can solve the system using linear algebra. You know what the solution, what the optimal solution is. Of course, what's gone on in machine learning is nowadays, we don't care whether things are analytic or not. We run very, very large scale stochastic optimization algorithms to try and find solutions that are often not unique. But a statistician would care a lot about that sort of, historically would have cared a lot about that, but still do today, about the uniqueness of a solution and the analytic nature of the solution. So I kind of think that machine learning then feeds into two different areas that are of interest for us. The first one being the primary one, I think data science arises from the fact that we now capture data by happenstance, right? So that it's a result of, oh my goodness, I've got all this data, happenstance data. It's a new thing. That's the big data phenomenon, that we've got so much happenstance data and we want to get value out of it. No one would ever have thought of that 120 years ago. At that time, that quote comes from, lies, damn lies, and big data, because getting data was expensive. It required someone with a clipboard to go out there and collect data. Of course, some data was just being automatically collected, which is like accounting data, but you would still have to go and read it. It would cost a lot of money to get data. Now it costs no money. And that's the big shift, right? And that's where the field of data science arises from. AI, I think, is a different field. It's been around for ages. It's always about, oh, can we get computers to do things humans can do? I mean, in a weird way, a sort of shifting target as like once they play chess, okay, that's not actually a human thing. Playing chess, you know, we move the target every time the computer gets better than us. So emulation of human behavior. Now that isn't actually necessarily something that you would have to do via data. I mean, the machine learning philosophy is that you would need data to do that. But historically, a lot of AI was done without data. It just happens that the best way of doing AI at the moment, the most successful way, is machine learning, right? It's not baked into the philosophy, whereas it is with one. So this is one reason why you see machine learning so dominant, because it's the driving technology between these two different fields. But if we were here 15 years ago, we would say data mining is the driving technology of data science, but perhaps we wouldn't be using the term data science so much. Okay, so the connection between these two is sort of through the Internet of Things. So in some sense, that term where everything's wired up. So not just the Internet of Things, but, you know, mobile phones and everything. And that's something I think you have to really watch out for, because I really don't like this term, Internet of Things. It's an Internet of people, right? And that's something you really have to remember when it's happenstance data and this data is being so easily collected, because this term Internet of Things is implying that there's just stuff you're looking at. Whereas much of the time, the stuff you're looking at is somehow associated with people. And talking about Internet of Things gives you the impression that it's all right that you're not thinking about the implications of the things you're doing, because you're just doing it to things instead of people. And it's interesting how often that language emerges in computer science, but also in law. So if we go back to this, anyone know how this is more widely called nowadays? This is legislation from 1981, 28th of January. GDPR, yeah. And what does GDPR stand for? General Data Protection Regulation. Very good. So where does it say in that, which is the first piece of GDPR legislation, that data needs to be protected? Data isn't endangered. We don't have to put data in special compounds, allowing it to reproduce. It's exactly the opposite. This is the original title, Convention for the Protection of Individuals with regard to automatic processing of personal data. And actually what it emerges as is individual data rights. If you look at what the GDPR gives you, it gives you rights around your personal data, the right to delete your personal data, the right for explanation. So it's appallingly named legislation. And it's this contraction of this original term. And it's suffering from that same thing, that we're protecting data. And, oh, sorry, GDPR can't help you. No, well, actually, it's people protection that is the purpose of GDPR. Okay, so I'm going to skip that. And then just sort of think about, I mentioned this briefly last time. I sort of said, well, how do we think about data science and why is it hard? Because I said that I've never seen data science done well. And the reason I hinted at is this notion that data science is not like programming. So we have a lot of good processes that we've picked up since the late 1970s about how to deal with what's called the software paradox. So Dijkstra was talking about the software paradox, I think back in the maybe late 60s, early 70s. And the idea was that, how did he phrase it? So, he said before we had fast computers, you know, basically software couldn't be complicated. It could only be simple. And as we've got faster and bigger computers, software has become more and more complicated because you could write bigger programs. And so in some sense, software development has slowed up. And now we have the same thing with the data, right? We have this data paradox that we've got such massive data, and understanding how to manipulate and manage this data. Before we had the data, it wasn't sort of a problem when it wasn't driving decision making. So I tend to think of that and think about the processes software engineering went through to get over the software paradox, to write code in a way that we would construct a modern system today, which is how you are taught as computer scientists. And if you go into a company, we can write very large systems that are reliable. And we have different approaches to doing it if you're in aerospace than if you're in cloud computing, sustaining the website of a social media giant. Of course, they do fail sometimes. Aerospace less often than WhatsApp. But there are a bunch of processes in software engineering that have evolved over decades to help us do that. We don't have such processes. And that's particularly difficult because of this point here that data science is far more like debugging than it is like programming. So what do I mean by that? I mean, let's say that I find a USB stick on the ground, and for some reason, I know there's some really valuable library code on that USB stick that we can assimilate into our production system for selling sweaters that is going to give us a lift on the percentage of sweaters we sell, and we'll all become rich as a result. And so I give you that USB stick and say, integrate this code in our production software system. And as a software engineer, what do you say? You say it's unsafe. You basically say, no, I'm not going to do that. That would be unsafe. Because where's that code from? Who wrote it? Who's controlling it? Is it malicious? Okay, so what's the difference between that? What you would actually do? So if I force you to do it, say if you don't do it, I'll fire you, and like you're stuck in this job. So you're forced to do it. How do you do it? Really carefully, right? So you would do a lot of time looking at the code, trying to understand which part of this library is it that's useful and which parts could be malicious. Can you lock down the essence of this library to something that you can control and deliver in lifting the sweater cells? And what is that essence? Now, that's kind of debugging, right? That's sort of looking at the library and understanding what's in the library. And by the time you get to the end, when you're finally certain, what you will really want to do is you'll sort of say, this is the library call you need. It'll be like one line. Call this REST API with these things. I've written an interface to it to stop you making the damaging calls to that REST API, because even that REST API that I can't change could be damaging. And so you give me one line of code and the USB stick back, right? And then what if I follow up by telling you, oh, by the way, someone can edit the code on the USB stick remotely. So all your good work you've gone to, actually could be undone by the fact that the code's going to change on the USB stick. That's data science, because that code is the data that you are now relying on for your decision making. And the API call is, what is my machine learning algorithm that I'm going to deploy on that code? So imagine that that's what we're doing in deploying, and see why we're in such a mess, right? So one of the things that I think really emerges from that is, and I don't know how to do that well, just like no one else seems to, but there's a few things that become really clear. It's really important you document your process of debugging, right? And share what you've included, what you've ignored, so that when later someone comes along and looks at that and says, I have to revisit the decisions that were made here, they understand your narrative in terms of why you made those decisions. So one of the outputs from your project is going to be a narrative. And that's going to be the main thing we're marking, right? The thing that makes it clear why you did what you did, right? We're not really going to care that much about, you will all, because you're all good students and you want to do well, you'll all be keen. There's just a natural embedded desire to build machine learning models that are accurate. You'll all want to do that, I suspect. But we're not going to be measuring you on that. That will be part of the fun of it for you. What we're going to measure you on is the decisions you made and why you made them, because that process of debugging is really the sort of key process in data science. And it's too often neglected because, of course, that process doesn't get integrated in the Git code repository, just as one line does. And we have no idea why that line, and why is there a comment there saying, never set lambda greater than 4. Right? I mean, there's another really nice paper called Performative Prediction that explains even when you deploy these things, if you're at the scale and size of Google, the scale and size of Google, you deploy your machine learning algorithms, you actually change the way the data works. So actually by making, sometimes it's you that's forcing the library code to change. Okay, so what you find is that when you talk to people, anecdotally, 80% of time is being spent on this data wrangling, this notion of like getting the data ready. I mean, and actually it's not even, there would be this other bit to data science that I didn't even mention. What we're talking about there is what I call the assess stage, is the debugging stage. Before that, there's an access stage, which is how do I even get the data on the USB stick, or how do I get it electronically loaded up? And in that stage, there can be more, you know, because the questions we didn't talk about there is what are the legal implications of whose library code is that, right? Where is it coming from? Are there any sort of copyright issues around that? Are there ethical issues of that library code is relating to people, personal data, GDPR? By the way, I like thinking of GDPR is General Data Protection Regulation, but I like to think of it as standing for good data practice rules, because if you look in what the GDPR says, you'll find it says a lot of nice stuff about which you would like to be true of your system. So I've got some lessons in here about when you're doing analysis. So one of the things is writing test code as you go. And that includes doing things like little sanity checks of little statistical tests where and when you can. So before you do something complicated, always do something simple. Make those tests accessible and document them. They are not quite the tests that you would normally write for regular code. So I don't mean like do software engineering testing. It's more like, oh, a little bit of code that checks this assumption I'm making about the data, right? That type of test. So probably test is not a word I should use because it probably draws you in the wrong direction. Be constantly skeptical, like we were before, around what's AI doing above machine learning? Oh, there's an error in there. There's something fundamentally wrong in where the data is coming from. Develop deep understanding of the best tools. So we're going to focus on a few tools, try and keep things narrow because, you know, as a data scientist over time, you would broaden your scope on the tools that you would use, but we don't have time to get you all into all the different tool chains. And I'm not a practicing data scientist, so I don't know the best tools currently. Share your experience of challenges and have others review work. You're going to be in the lab. Obviously, you can't copy each other's results, but there's nothing wrong with chatting about all the sort of things that you've imagined or seen in the class or tools that you found. It also means when you are managing a data science process, so this is less perhaps what you're doing now, but a lot of people will have done internships or may have been at companies. One of the challenges in data science being done badly is they are just integrated into agile software development. So by which I mean that there's a Scrum format, there's 2 weeks where everyone's saying what they're going to do, then they're reporting at the end of what they've done and how they failed to do it, et cetera, et cetera. The reason why that's quite problematic for a data scientist is because there's something called the explore-exploit trade-off. So explore-exploit trade-off is this issue where if I give you a task, the first thing you're going to try and do is work out how to perform the task, right? So if I say, fit linear regression on this data, you probably type into Google linear regression, fit linear regression on camel data. You might type into Google linear regression camel data. That might be the first thing you do, right? But then you'll poke around. You try and find a few different ways of doing it. You won't necessarily just read the first result, which would be some idiotic towards data science article with some naive understanding of the world embedded in it. Actually some of them are quite good, but I just find it really irritating that you only get medium articles on Google nowadays. But so towards data science probably has some very nice articles on it. Then you're going to spend a lot of time looking through that, maybe asking people, trying things, coming back. If I give you 2 weeks to do it, you'll do that. If I say do it by tomorrow, you're going to find the first hit that seems to do anything vaguely similar and get on with implementing it to get it done, right? that time frame is what drives the so-called explore-exploit trade-off. It's what you are learning to manage as undergraduate students, for sure. And as PhD students, you end up learning to manage that over year-long periods. As undergrads, you're learning to manage that over weeks and whatever. When should you stop reading about something and start doing it, right? So actually, by the time you get to a software engineering company, everyone's really good at handling that independently. They can do that themselves. And I think Scrum is just there to sort of give you a metronome beat around that process, allow you to decide what you can do by next week, share it with others, and complete that. Unfortunately, that metronome beat of 2 weeks is fine for software engineers in this modern world where we understand how to do it, and absolutely rubbish for data scientists or scientists, because it doesn't give you enough time to do the explore stage before you're required to, yeah, this is what I've done. I mean, the thing I've experimented when managing in this space is 4-week periods. So extending it so that you sort of have 3 weeks to mess around with the data, because even getting the data, and it's because we don't know how to do these processes. And then the other problem you get is that the data scientists often left alone and assume they're just going to do things because no one understands their job. And that's really depressing for the data scientists. So making sure software engineers and domain experts, because domain experts are really vital for data science as well. Data scientists are always having to bridge. We wouldn't have known that it was stupid that machine learning crossed AI if we weren't people who are expert in these sort of terms. But if you're not looking at things that are on Google, if you're looking at climate, or if you're looking at a physics system, if you're not talking to the physicist or the climate scientist about what things are stupid, you're not spotting those problems. So you have to really bridge these two sides. It's a really difficult job. Right. I've got this thing on complexity and action that I don't have enough time to run through today. So I'm going to stop there and just see if there are any questions, and I'm going to stop the recording as well.